We will now look in detail on how does distance vector dynamic routing protocol works. Okay, a quick recap on how does dynamic routing protocol works. So a router will send and receive routing informations through its own interfaces. So the router they are connected together, they will share routing messages, routing informations if they are running the same routing protocol. Okay, what are these routing messages or information? This is for the routers to learn about the remote networks. And when there's a topology change, the router will then detect the change and advertise this change to all the other routers so that they get the most up-to-date routing information. Okay, let's look at how does distance vector routing protocol works. Okay, first, during cold start, the router boot up. Okay, the interfaces were configured with IP address. No shell command was issued to bring up the interfaces. Okay, then what happened to the routing table for these three routers? R1, R2, and R3. Okay, for R1, okay, two directly connected interface. In the routing table, for R1, we will see the two networks, the 10.1.0.0 network and 10.2 networks. Okay, 10.1 network connected to the FA00 interface, 10.2 network connected to the CA00 interface. Okay, same for R2, two networks, the 2 and the 3. Okay, 10.2 and the 10.3 networks. 10.2 network connected to CA00, 10.3 network connected to CA001. Same thing for R3. Okay, the 10.3 and the 10.4 network and the interfaces. Okay, we have the matrix here because you are running RIP. Okay, so it's based on hop count. This two network is directly connected, so it's 0 hop away. For R2, these two network directly connected, 0 hop away. For R3, same thing, 0 hop away. So for directly connected network, the number of hops or the matrix is always 0. Okay, next, let's look at how does the three routers learn about the remote networks. Okay, they learn through exchanging routing updates. Okay, the router will exchange routing updates. Okay, so for first, let's say R1. R1 will send a routing update to R2. In the routing update, it will contain these two networks. Okay, the two directly connected network, 10.1 and the 10.2 to R2. So R2 will check 10.1, is it in his routing table initially? Okay, let's highlight the initial routing table so that it's clearer. Okay, this was the initial routing table for R1. This was the initial routing table for R2. And this is the initial routing table for R3. Okay, so these two networks were sent as routing updates to R2. R2 will check 10.1.0, is it in his original routing table? It's not. So he will add this to his routing table and he will add 1 to the number of hops. It will now become 1 hop away. Meaning if this router receives a packet going to 10.1 network, he will send it out through 000, the exit interface, and this is 1 hop away. So R1 will receive the packet and forward it to the 10.1 network. Next, he will also receive this routing update from R1. And you will check his routing table. Do I have this network? Yes, I have. So I do not need to add this network to my routing table. Okay. So next, R2 will send the routing updates to R1. And it will contain these two directly connected networks. So R1 will check, do I have 10.2? Yes, I have. So no need to include this route to my routing table. 10.3. Okay, 10.3 is something new. So it's not in my original routing table. I will add 10.3 to my network. The exit interface will be 0.0.0.0 and it will be 1 hop away via R2. So this will be added. Okay, so by R1 exchanging route with R2, okay, one new route will be added in R1 and one network will be added to R2. Okay, now the same things will happen between R2 and R3. Okay, so R3 will also send a routing update of these two routes to R2. So R2 will compare 10.3, I have 10.4, I don't have. So I'll add 10.4 to my network, and it will be via my serial 001 interface going to R3. Okay, how about R3 now? R3 will receive the route for 10.2 and 10.3. Okay, it will receive it. Okay, do I have 10.2? I don't. So what will R3 do? R3 will add 10.2.0.0. Okay, and connected to my serial 001 interface. So I will send the packet out through my serial 001 interface if I need to send anything to 10.2. And how many hop away? I will increase by 1. So 0 plus 1 will become 1. Okay, so now one new network will be added to R3. Okay, so this will be the routing table when R1 first exchange route with R2 and when R3 exchange route with R2. Okay, after the initial exchange, the network have not reached convergence yet. Okay, because there's still some remote networks that the routers will not know. Okay, let's highlight the routing table again. Okay, this was the routing table after the first exchange of R1. Okay, this was the routing table for R2 after the first initial exchange. And this was the routing table. Okay, now R2. Okay, let's look at R2. R2 now, during the second exchange, will send this whole routing table to R1. And also send this routing table to R3. Okay, why? Because he noticed that, oh, okay, initially I only sent 10.2 then 10.3. Now I know two more networks. I better inform my neighbors now about these two networks. Okay, so now initially I only sent 10.2, 10.3. Now I also send 10.1, 10.4 to my two neighbors. Okay, what will R1 do? When he receives this routing table, he will check 10.1 I have, 10.2 I have, 10.3 I have. Oh, a new one, 10.4 I do not have in my routing table. I will add this to my routing table and I will increase by 1 the number of hops. So now to go to this 10.4 network, the exit interface will be serial 000. The packet will exit here and you'll reach the 10.4 network and it's 2 hop away. 1, 2 hop away to reach the network. Okay, the same goes for R3. Okay, R3 received the entire routing table, the new one from R2. He will compare, he realize 10.1 is something new, and it's again 2 hop away. Okay, so after this, okay, we'll have achieved convergence. Okay, which we will look at in the next slides. The routing table will have stabilized. Okay, next, distant vector routing protocol use split horizon to avoid loops. Okay, what is this split horizon? Okay, split horizon basically means that information that will not be sent out from the same interface where it was received. Okay, let's look at here. Okay, R2 received this information 10.1.0 from R1, correct? He received this information from R1. So this information will not be sent, this entire route will not be sent to R1. Okay, this entire will not be sent to R1. Otherwise, if this route is sent to R1, R1 may have another route here. Okay, 10.1.0.0. Okay, and in this case, it will be serial 000 because it received from R2. And how many hop? I need to plus 1, it becomes 2 hop away. Okay, obviously, this route will not appear in the routing table because R1 have a better route, 0 hop away. Okay, but what happens if this link goes down? If this link goes down, this new route may appear in the routing table. When this new route appears in the routing table, R1 will send a packet to R2 if we receive a packet going to 10.1. So you will send the packet to R2. Okay, if this packet is going to 10.1, what happened to R2? R2 will send it back to R1. And R1 will send it back to R2, R2 will send it back to R1. This may result in a routing loop. So to prevent this, this particular route will not be sent as a routing update to R1. This one will not be sent to R1, but this will be sent to R3. Which one will not be sent to R3? This route will not be sent to R3, because how does R2 learn about this route 10.4? It was learned through R3. So because it learned this route from R3, this will not be sent to R3. Again, for the same reason, to prevent routing loops from happening. Okay, after the second exchange of routing update, all the routers notice that the routing table has stabilized. And now, every single router will have a route to every single network in this topology. So let's count the number of networks here. We have one network over here, a second one here, a third one here, and a fourth one here. So notice the routing table for R1, R2, and R3. All of them have 4 networks. Okay, so once this routing table has stabilized, okay, the network have converged. Okay, we will use this term called convergence, achieving convergence, when all the routers have complete and accurate information of the entire network. So convergence is the time it takes for the router to share information. Okay, obviously the lesser the convergence time, the better. That means it takes lesser time to converge. So routing protocol will be rate based on the speed to convergence, how fast it converges. The faster it is, the better the routing protocol. Okay, distance vector routing protocol helps to share the update between the neighbors. And this router use distance vector. They are not aware of the entire topology. They only know the routes from their neighbors, from their immediate neighbors. They only know the routing table of their immediate neighbors. Are they able to block out the entire topology? They are not able to. Later we'll look at this link state routing protocol. Link state routing protocol is aware of the entire network topology and calculate the best path based on the network topology. Okay, we will look at that in link state routing protocol. Okay, some distance vector routing protocol send periodic update. That means on every maybe 30 seconds, I will send you my entire routing table. Every 30 seconds, I will send you the routing table again. So it's periodic. Okay, so for example, RIP version 1 and RIP version 2. Okay, they send periodic updates. For RIP version 1, the update is sent as a broadcast. RIP version 2, ERGRP, they send as multicast. Okay, multicast is obviously better because only RIP router will receive the multicast. If it's a broadcast, every single PC, computer, printers with IP address will receive the broadcast, which is not so good and not so secure. So RIP version 2, ERGRP will use multicast address. Okay, ERGRP is slightly better. It's an improvement to RIP because it can also use unicast if you only want to send the update to a particular neighbors, rather than always use multicast. So you also have to save bandwidth. And ERGRP will only send update when it's needed, not periodically. So only when there's a change in topology, I will send the update. I will not send the update periodically. So you also have to save the bandwidth. Okay, let's look at RIP as a distance vector routing protocol. It's very easy to configure, very easy to understand because it's based on hop count. But there's a limit. The maximum hop count is 15 hops, 15 routers connected in series. If anything more than 15, the network will be considered as unreachable. So there's a limit in the size of your network. Okay, for RIP, the RIP update are broadcast. RIP version 1 is sent to a broadcast every 30 seconds. Okay, RIP version 2 is an improvement. It's classless routing protocol. So it supports VRSM, CIDR. The update is sent using a multicast address. The routing entries, it can be reduced if you use route summarization. And it's also more secure, so it's a support authentication. Okay, so RIP-ng is created to support IV version 6, but the same limit of 15 hop counts also apply, and the administrative distance also the same, is 120 for RIP-ng, RIP version 2 and the original version RIP. EIGRP is another distant vector routing protocol. It replaces the IGRP in 1992. You have a lot of features as compared to RIP. Okay, one of the main features is it sends bounded and triggered update, meaning it only sends updates only to the router that need it. Okay, bounded and triggered means only when there's a change. No change, no need to update the neighbors. So you only send the required updates only to the router that need it, bounded trigger updates. The second feature is it uses a hello keep alive mechanism. Because it only sends bounded and trigger updates, so sometimes no updates, you need to know that the neighbors are alive. So they will send hello messages, very small little messages that send periodically to make sure that the neighbors are alive, the link is still running. So they uses hello keep alive mechanism to make sure that the neighbors are alive. Next, it maintains a topology table. Okay, and this table very different from routing table. The topology table contains all the routes received from the neighbors. Routing table only contains the best path. Any redundant path, it will not be stored. But topology table store both the best path and the redundant path or alternative path. Because it stores the alternative path, EIGRP can achieve rapid convergence. Meaning if the best path goes down, it can immediately bring up the backup path. So you can do rapid convergence. Okay. And finally, it supports multiple network layer protocol, IP version 4, IP version 6. Why? Because it uses PDM, protocol dependent modules, to support different type of layer 3 protocols. So EIGRP is considered a very enhanced distant vector routing protocol. We'll look at EIGRP in the EIGRP chapter. Okay, when we cover EIGRP next term.